All right, let's look at some properties of circles. All right, first one, the perpendicular bisector of any chord passes through the center. All right, so let's draw a picture. So you have a circle, and AB is just any arbitrary chord. If you draw a perpendicular bisector, so say pick a midpoint, you can call that M or something like that. Then draw a perpendicular line. So draw a perpendicular line, and you see that this perpendicular line will automatically goes through the center of the circle. Right. So let's quote the perpendicular bisector theorem. So let's call this this guy L. Right. Perpendicular bisector L is a collection of points which is equidistant from A and from B. So AX equals BX. And since O is the center, the OA distance between O and A would be a radius. So from here to there, and from here to there, those are radii. So we know that AO equals BO, right? So which satisfies the condition here, which means that therefore O is in the perpendicular bisector, right? So this will verify number one, right? And number two, a line passing through the center and perpendicular to the chord bisects the chord, right? So let's do that. All right, so we're drawing a line through the center and a perpendicular to the chord. So you're gonna draw that. So we know that it's already perpendicular, right? Then what we can do is try to establish, this is actually, the proof is homework, but I'll just give you the idea. All right, so draw a triangle here, and triangle there. All right. So what you can do is to we need to show that this point right here is a midpoint M, right? So we have to show that this length here is the same length there. So we don't know that yet, so I'll put the question mark there. Right? But we can establish that by looking at these two triangles. So here is the right triangle here, and here's the other right triangle, right? And we know that these are going to be congruent by this criteria. You can see that here is, we don't know that this side, but we know that here is the angle. We can probably use angle here. Since OA and OB are congruent, we have isosceles triangle. So we know that these two angles are congruent because these are base angles of an isosceles triangle. So we can do angle, angle, then side, because those are radii. So we can do angle, angle, side to establish the congruence between these two. And since AM and BM are corresponding parts of congruent figures, therefore they're congruent, which means that this line bisects the chord. Right? So you have to write the formal argument as a homework. So this is number 2. Right? Number 3 and number 4 are the proofs are in the book. So I'll just draw a picture, and we can kind of make sense out of it. Right, so two congruent central angles subtend congruent chords, and conversely. So okay, so let's say if you have a congruent, so this is congruent to that, right? then the AB is congruent to CD, right? So we can easily establish the congruence between these two triangles, right? Because OA, OB, OC, OD are all radii, so they're the same length. So you can do a side, angle, side to do this implication. Side, angle, side, right? And the other, so this is true for converse. Converse would be if you have congruent chords. So if AB and the CD are congruent first, if you knew that first, then what you can do is, so in this implication would be, we can use a side, side, side. So S, S, S to establish a congruence. Therefore, these are corresponding parts of congruent figures, right? So that's number 3, right? All right, let's look at number 4. Two chords equidistant from the center have equal length, and conversely, right? So let's do this direction, right? Alright, so let's draw a bunch of radii. So it's O, let's say OA, and OB, and OC, and OD. And we know that they're all radii, so they're the same length, right? And also these two have right isosceles triangle, so we know that these are all congruent here and there, right? Then each of these 4 right triangle here, that one and that one, they're all congruent by hypotenuse and the leg, because there's a right triangle, so it's HL will give you a congruence, right? So therefore we know that let's see, have equal length. So look at this is congruent to that, and this is congruent to that, this is congruent to that. Of course 2 of these is equal to 2 of those, right? So we got equal length. For the converse, right, so we don't know that the equidistant, but we know that they have the equal length. So let's say AB and the CD have equal length. So you already know that this is congruent to that guy to begin with. Then we have to show that this is equidistant from the center. These are equidistant from the center, right? So what you can do is pretty much very similar to before, but since we have a side, 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 we can establish the congruence between these two, right? And also this is isosceles triangle. We definitely have this angle is congruent to that. This angle is also congruent to that, right? So then what you can do is we can draw a perpendicular line from the center. So we know that that's perpendicular. And then it's a perpendicular here. Then we can show that these 4 little triangles are again congruent by, right? We can also we can use angle. Let's see, angle, side. Okay, angle, side. So we can just do angle, side, right? Or you can think of it as we can think of it as a HA, hypotenuse and angle, right? But anyway, once you get that, this is corresponding to that by corresponding parts of congruent figures. We have the equidistance there, right? So number 4 checks out, right? That's it. I hope that this was clear.